here.
Faraday applied for a job at the University of Toronto.
Say that again?
Didn't apply for a job at the University of Toronto.
I don't know, did he?
And he was rejected. He was not
Who,
selected.
Faraday?
Yeah. Yeah, I think so. He's
I don't know much about his life, but except he wasn't trained as a scientist in any way, so he had no formal training.
That was one of the reasons, perhaps.
Right.
So if you're okay, we'll start.
He was not taken seriously.
Okay, we should start. Good afternoon, everyone. Welcome to the Warren Lecture Series. Today I'm very pleased to introduce a speaker, Professor Paul Martin from Colorado School of Mines. I got to know Paul through correspondence long ago, maybe, I don't know, 20 years ago, when I wrote him a letter, as Paul reminded me that there were no emails at that time, requesting one of his papers. At that time, Paul was in England, and he replied. Actually, only two people replied to me. It was Paul Martin and Tom Cruise, who was a founder, in some case, of boundary element method. But anyway, Paul moved to the United States, to Colorado School of Mines, as full professor in 1999. Previously, his education is all in Britain and England. He has his bachelor degree from University of Bristol and PhD and the master's degree all in mathematics or applied mathematics from University of Manchester. And he worked there prior to coming to Colorado School of Mines. Paul has an amazing productivity. His list of papers, peer-reviewed papers on his website, I counted 134, and all in top journals, Proceedings of Royal Society, whatever, you name it. So in addition, Paul published a book. So his area of expertise is in wave equation, hypersingular, in integral equation in general, in solid mechanics, fracture mechanics, and Paul is an editor for two journals, and quarterly journals of mechanics and applied mathematics, and Siam Journal of Applied Mathematics, right? And he's also associated editor for two other journals. And I think it's enough for this brief introduction, so please join me and welcome a speaker.
The best way to have lots of publications is to be old. So, well, thank you very much for that very enthusiastic introduction. Okay, so I'm an applied mathematician, and at my stage of life, many of the things I work on are based on problems that people give me to do. So this is a problem that started life like that. So somebody came and asked me about this problem. Everybody knows about a Faraday cage. How does it work? And how does it work in theory? Can you show that it works in theory? And so that's partly what this talk is about. So here we are. Everybody knows Faraday's cage, right? So do you all know what Faraday's cage is? So Faraday was an amateur scientist, right, and came to the attention of Humphrey Davy, who was the inventor of the miner's lamp. Maybe you know this. But then he became an assistant, and then he got a job, and he became the director of the Royal Institution, which is a thing in the middle of London, in Piccadilly. And he was a great experimentalist, but he had no clue about theory. He couldn't do anything in mathematics, which was not a problem for him. But this quotation here is evocative of what he used to do. So one of the jobs of the Royal Institution is to enhance nowadays we would say one of its jobs was to enhance the public understanding of science. Right? So outreach, if you like, and that's probably the current buzzword. So he would do experiments that were intended to illuminate the public's understanding of science. We're talking about the early part of the 19th century. So the Faraday's cage he demonstrated in around about 1835, I think it was. So what he did was he had a kind of a wooden shack, which was in the lecture room, and it was covered in metal sheeting. And then he would go inside this shack, like it says here. So he'd send someone in carrying a frog or a rabbit or something, and then you would see like a giant, like a Van de Graaff generator, and there'd be these huge sparks that would come down like this and hit this shack, and they would walk out unharmed, of course. And this was a big surprise to the audience that you weren't killing these people. One of the things that people were interested in, especially in the 19th century, was lightning and the effects of lightning. So they knew lightning was bad, but they were not so sure what to do with it. Okay, so if you go on the web, you can quickly find crazy pictures about Faraday's cage. So here's one. So here's some idiot in this. He looks like an idiot, right? In this cage, and these giant sparks come down. I think someone told me this is a Tesla coil. I think that's what they're called. I don't know what it is. I just like the picture. But you see that it is actually a cage. He's in a cage, right? So it's not the way that Faraday had this set up was that you had a complete metal enclosure with no holes, no gaps in it. Not a cage, just like living in a sphere. If you want to live in a mathematical world, right? Everything's a sphere in mathematics. So, if you want to find out how it works, of course you go to Google. This is the first thing you do, right? You go to Google, and so here's an explanation that I just picked off of some web page in Google, probably Wikipedia. And so what it says here, or maybe I'll just read it. So Faraday's cage operation depends on the fact that an external static electric field, so this is the stuff that you're seeing coming in from the outside, will cause the electrical charges within the cage's conducting material to redistribute themselves so as to cancel the field's effects in the cage's interior. So as a mathematician, I don't really understand this, but I'd like to be able to show this more theoretically, right? And so that's partly where I'm coming from here. So this is the standard explanation, and it assumes that you have a perfect conducting object here with no gaps in it. So think spherical shell, right, or shed that's been encased in metal foil. This is Michael Faraday here on a £20 note in England. So he's a pretty famous guy, at least in England. I'm going to try and explain some of how I'm going to model this problem, and I'll do it in two areas. So there's the electric application, which is static electricity. So the governing equation there is Laplace's equation. And then in acoustics, so here you would be thinking either about sound waves, right, or in some representations you can think about Maxwell's equation, so electromagnetic radiation, but there are waves now. And so here the governing equation will be the Helmholtz equation here. Okay? So that's where we're going. So first of all, then, I need some kind of model to how are we going to start, right? So one way to think about the model now is also old, so this goes back to Hertz. So you know who Hertz was, right? He was the guy that showed that there were electromagnetic waves, right? So he was interested in experimentally showing that there were electromagnetic waves. And one of the devices he used in experiments here is this thing at the top here, which is sometimes called a mouse mill. You can imagine a mouse running around in this or a hamster, right, running around trying to make this thing move. But what it's made of, it's parallel wires, right? Thin parallel wires, and they have been arranged so that they all form a big circle with all these parallel wires going through it. And you can see the picture at the top there. And this picture I stole from this book. This is, if you like, this is the standard book on lightning, written whenever it was, 1892. So it's still in print, this book, if you want to look at it. Oliver Lodge was Sir Oliver Lodge, so he was a physicist. He spent a lot of time as a professor of physics at the University of Liverpool in the north of England. Okay? Famous for one of its football teams. Not as famous as the one that comes from Manchester, or ones that come from Manchester, where I came from. Okay, so this is, if you like, one motivation for the model, but of course it's a mathematical lecture, or some of it's going to be mathematical, so I need a clean mathematical model. I'm a mathematician, so I'm allowed to have clean models. So this is what we'll be talking about, right? So the idea now is that we have a large circle, or a radius, I call it B, so I'll call this the ring, right? And then around the ring, there are all these black dots. So these are meant to be the cross sections of the little thin wires, right? And they're going to be equally spaced around the ring. And so there are N of them, capital N of them. And the problem that I'm going to look at here and discuss is, you see, think about the cage. So in the cage problem, the basic theory says there are no gaps, right? There are no holes, right? So what I'm interested in is what happens as the gaps get smaller. So you might expect that if I just had one wire, this is not going to do anything for me, right? If I have two wires, maybe it will do a little more. But really, I want to have lots and lots of wires. I want to have a representation for a cage, right? And so the mathematical question that you can investigate then is what happens as the number of wires goes to infinity. So think about n getting large. Okay? And so what you might hope, so this is your intuition now, is that in the limit, right, as you let the number of wires get very large, you might expect that all the gaps get filled up, right? And so this ring will behave as if it is a solid ring, right? A single conductor, right? A single scatterer in the context of waves. So that's the question, right? Does it converge to what you think you're going to get, right? But perhaps more interestingly is how fast does it go, right? So let's suppose it does approach the right answer, the expected answer in the limit. How fast is that limit, how fast is it achieved? And we'll see that the rate of convergence here, which is the kind of the meat of the mathematics, if you like, is very slow, right? And it's surprisingly slow. But we will see. There's no really hard mathematics in this, I hope, but we'll see. So first of all, if we're going to say, I want to find out what happens as the number of wires goes to infinity, I need to know what the limiting problem is. So I'll just talk a little bit about the limiting problem. So this is where you have a complete ring with no gaps, no little wires, just a complete ring. So this is really to set up the notation. Now I use this physical pointer, which is excellent. So the problem now, this is the acoustic problem. So this is the one where you are solving the Helmholtz equation. We're in 2 dimensions here. This is a 2-dimensional problem. So the unknown function is this u. Here are the polar coordinates. So I'm just doing the problem now of this is a textbook problem where you have a plane wave and it comes in and it hits the circle of radius b and you compute the scattered waves. So you either know this or you don't, but this is kind of standard material. This here is a plane wave coming in from the left. The time dependence, which I didn't bother to write down, is e to the minus I omega t. Omega is the frequency. And then this term here, right? These are Hankel functions, the special functions. These solutions represent the waves that are scattered, and so they're going to be sent out to infinity. So the first time is the instant wave. The summation gives you the effect of the ring. And here the problem that we'll look at is where the boundary condition is that u equals 0. So in the language of acoustics, this would be a soft ring. So I have a large ring here of radius b. Right? The ring is complete, so ignore the dots for the moment. If I apply the boundary condition here, this is just an exercise in separation of variables. You can figure out what these coefficients are, and they have this horrible formula. But then the question then that we're going to be interested in is what happens when the number of wires, which are equally spaced, if I try to represent this problem by having lots of little wires, does it get to the solution of this problem, right, which is explicit, as the number of wires goes to infinity? So I show you that just partly to show you the notation. And then the corresponding problem for in electrostatics, now it's Laplace's equation. I use capital V now for the potential here. I use this in deference to Maxwell. We'll see Maxwell in a minute. So now the problem is simpler. It's just Laplace's equation. And so you have to decide, well, what's going to be what's taking the place of the incident plane wave. So I'll just take a simple uniform field at infinity. So I write down the solution like this. So this term here is the uniform field at infinity. Right? To get the actual field, I take the gradient of V, right? It's a potential. So this is going to give me the uniform field at infinity, and this part here is, if you like, it's the image term, right? And so this part here takes account of the fact that we have a large circle of radius b on which the potential is 0. So you see that these two problems are kind of analogues of each other. There's one for the Helmholtz equation, one for the potential equation, right? And which one you like depends on what you feel most comfortable with. Okay, so these are the problems. I want to find out what happens when these number of wires goes off to infinity. So first of all, so as far as I know, this seems like an obvious problem to study, but the literature is very sparse on this, and I'll say a little more about that as we go along. But the kind of related problem here, which is very classical now, and this does go back to Maxwell, is the problem where you have an infinite straight line of wires. So now I have a straight line with all these black dots arranged like this periodically, going off to infinity in both directions. So you go to Maxwell, and you say, tell me about this problem, Maxwell. So you find this problem in his, so this is there's a famous 2 volumes treatise, I guess, that he wrote in the middle part of the 19th century. And so we think of those things, no one really looks at these books anymore. You kind of think of them as they're the place where Maxwell's equations were first written down, right? But there's lots of other stuff in these books. And this is one thing that he writes down. This is a picture taken from his book. Right? It's astonishing to me that he could draw pictures like this in those days, right? Compute pictures like this. So this is just a copy of his book, from his book. So you see this formula here. So this is a rabbit out of a hat, right? Which is kind of how they did things in those days. They just write down a function and say this is the function that does the problem, right? There's not really a derivation. Okay, so now let me try and talk about this function here. It's kind of interesting, right? So here, capital X and capital Y think of them as Cartesian coordinates, and in terms of my picture, so I mutilated his picture by drawing these lines on it. Right? So the y-axis, so the idea is that in this direction, there's going to be an infinite periodic row of wires. Right? So one of the wires is here, right? And then there's the next one, right? And then it's periodic in the y direction. In the x direction. It's kind of perverse to have x going this way, but that's how it is. Okay? Y is the coordinate perpendicular to the row of wires. Right? So this is so you write down this function like this. Okay? So the idea now is that if you go to the right, so you let y go to plus infinity, so you find out what's happening over here, right? Then you can estimate that log, and you find that it goes like this, right? So this bit here, right? This is going to be the uniform field, right? This bit here, you see, it decays really fast, right? It decays exponentially as you move away, right? So as soon as you're here, right, roughly speaking, this field looks like y, right, plus something very small. Right? If you go to the left, so now we're moving to this side, right, you see that the field is exponentially small. Right? Y is negative now, so it's exponentially small. Right? So that's why this is taken to be a representation for Faraday's cage, right, which says far to the right here I have a uniform field. Right? Then I have an infinite row of wires. Right? Out here, I don't feel anything. It's exponentially small, right? If you like, nothing gets through the gaps. Right?
I guess I don't understand the boundary conditions that you give me a axial symmetry along the x-axis and the solution's not so.
Okay.
To repeat question, because it's important.
So you've made trouble now.
I don't understand the boundary condition that it looks like we have a symmetric problem with
I didn't explain the geometry properly. So let me start again. So these little circles that you can have, so these are the wires. The wires are coming out this way, right? The field doesn't depend on that coordinate. It only depends on x and y, right? So there's nothing coming on this way, right? So the wires are coming out at you like this, right? And there's infinitely many of them, and they're arranged periodically in this way. So you've got one coming out like this, and then another one coming out like this. Right? Over this side, I have an ambient field, an ambient electrostatic field, right? And the idea is that, and it's a big field, right? Relatively big, right? So the idea is over here, you don't feel that field. The effect has been killed this is how the cage is supposed to work, right? It's been killed by the fact that you have all these little wires, and on these wires the boundary condition is that the field is zero, potential is zero. I must have written that down somewhere. Okay, so now maybe I finish off. So I take this field capital V, which is a rabbit out of a hat, and I notice that it has certain interesting properties, right? And then I say, well, if I want to build more solutions of Laplace's equation, this is the governing differential equation, then what I can do is I can do the following simple thing. I can take the thing I just wrote down, I can multiply it by a constant, and I can add a constant, right? And I still get another solution of Laplace's equation. Right? But now I can play with A and C, and also the scaling of x and y, so I can scale x and y. Right? I can replace big X by little x times some parameter. And then I can arrange, I can contrive that I can play with the constants so that, in particular, I can make it so that W, this new field I've just built, it's approximately zero. This is not an exact solution. It's approximately zero on little circles here. So this is meant to be a representation for the little thin wires I'm having. So you see, this is not really it's not really a general way of solving problems, you see, because I have to start off with this rabbit. I write down this field, capital V, and then I play with it a little bit. I make some small, I play around a little bit in order to satisfy the boundary conditions. Okay? But this is like 1860 or whenever this was done. But the idea is, you see, what you see is you have this exponential decay, right? And so this is something that so this, you might think then this is an explanation for why Faraday's cages work, why they work. But it's not so clear that they are. It's not so clear that this is the explanation. All right, so now I'm going to the way I'm going to talk about this first is I'm going to try and talk about the acoustic problem first, so the Helmholtz equation. This is because I feel more comfortable. But everything that I'm going to say to you now will also work for the electrostatic problem, and without much change. And I'll try and explain how it works as we go along. So here's the basic problem then, right? So now we suppose that we have n objects, right? So these are going to be the cross sections of the wires. We're in 2 dimensions. This is the time dependence. This is the governing PDE, the Helmholtz equation. So if I gave you that problem, so I said, here's n, let's think of them, they're going to be circles, right? But at the moment they don't need to be. But let's suppose they're circles. If I told you, here are n circles, and I tell you where they are, and I ask you to calculate the scattered field, I send a wave in, it bounces around between all these little circles and then comes out. How can I calculate what comes out? And that's a problem that you can do, right? So Sonia knows all about these kinds of problems. You can use various kinds of multipole methods. But we are going to be interested in n going to infinity, right? So knowing how to solve the problem exactly is not going to be very convenient, because it's going to be a complicated thing to do, right? If there are 1,000 circles and I ask you to solve that problem, that's just about doable numerically nowadays, but ultimately we're going to look at what happens when n gets large, very large. So what I do is I use this method called Foldy's method. This is an approximate method. The way this works is as follows, right? So I take this convenient person over here, right? And so Foldy's method works like this. Don't worry, I'm not going to hit you. So the idea is this. So a wave comes in, so some kind of field comes in and it hits you, right? And it's your job to say how the wave is going to be scattered, right? And so you do the following thing. So this is the formula. Let me look at the formula first, and then I'll come back to my scatterer. This is the total field, right? This is the incident field, right? So this could be anything. It doesn't have to be a plane wave. Any incident field that you can think of, right? So this field comes in, and then it hits the scatterer, right? So now this is where the approximation comes in, right? So in general, if I wanted to solve that problem, how does the field scatter, right? That's not a trivial problem to solve, even for a circle, right? I showed you the solution earlier on. It involved all those infinite series of Hankel functions and all that good stuff. So I make the following simple approximation, right? So first of all, I tell you that the scattered field only depends on this function here. Right? This is a Hankel function, but it only depends on the distance, right? So in other words, when the wave comes in, I'll leave the stick over here, so you'll be quite safe. So the wave comes in like this, right? And it's when you feel the wave, what you do is you sample the wave, right? So you take a measurement of the wave, that's this term. So I take the incident field and I measure it at some point at the end of your nose, right? And then you then scatter the wave. So you send out the same wave in all directions, right? It doesn't depend on angle. So what you feel is the same as what you feel, right? It does not depend on the angle. So you see no dependence on the angle here. It's just the field that gets sent out only depends on distance, okay? So that's what happens. So the idea now is that any wave that you can think of comes in, right? You sample it. So here I take the origin because you happen to have the origin, right? You measure the field, right? You scatter, you send a wave out. This is the wave that's going to go out. But also you have some flexibility in that you can decide how you can weight what comes in. So you can choose this number here, right? This G here is called the scattering coefficient. If you're a small scatterer, right? And that's what we'll be interested in because we're going to have lots of these little thin wires, then this is a reasonable model. In fact, asymptotically, it's a correct model. And the idea is that you will be small. So that means that this parameter Ka here, K is in the PDE, right? And A is the size of the scatterer. So as long as this is small, which is relevant for us, right? This is an appropriate model, right? Provided what the boundary condition on you is that you are soft, right? I'm not going to go there, right? That means that the boundary condition is u equals 0, right? Not du by dn being 0. So you have assumed that it's a soft object. Asymptotically, soft objects scatter the same way in all directions if they're sufficiently small. An asymptotic result. So the idea now is that Foldy's method, which we're going to come to, starts from this assumption. And then it says, well, okay, now I've got lots of people in the room, right? And you're all separate scatterers. Foldy's method tells you how to compute all the multiple scattering. You know, the wave hits one person, goes to hit you, then it hits you, and it comes around. So it will take account of all those interactions completely and accurately, assuming that the first approximation is reasonable. So here's something about Foldy. This is amusing as well. So Foldy was a physicist. There's a nice picture of him. So he arrived in the US when he was 2, I think. And then so he grew up here in Ohio. That's where he was studied. And then so he was born in 1920. So when he was 22, he went off to New York. And so this was part of the war effort. Right, so I'll talk about what that was in a minute. Right? And then he did his PhD with Oppenheimer, who everybody in physics knows, maybe everybody else. And then he spent the rest of his career back at Case Western. So that was his life. Right? But the bit that's of interest to us is what he did in New York. Okay, so this is in New York. So you'll recognize this building. So he was employed, and many young physicists and mathematicians were in similar activities. So he was working in an office in the Empire State Building, and there were many other well-known scientists. In particular, Joe Keller was there in the same group. If you know about Joe Keller, he's still around, doing all kinds of scattering and many other things. He just got his second Ig Nobel Prize recently. And do you know what the Ig Nobels are? He got one for a paper that he wrote in the Siam Journal on Applied Math on the motions of ponytails. Right. He's a runner, so he obviously likes following young ladies pondering the motions of. But we won't go there either. His first Ig Nobel was to do with pouring tea out of a teapot. Okay, so this was the problem that Foldy was working on, right? It was to understand how underwater sound is affected by the presence of wakes, right? So bubbly regions of the flow. So here this is meant to be done for two reasons, right? One is to understand what you're doing in your submarines, but also how to find other people's submarines, right? Because their wakes are making bubbles. Their machines are making bubbles. The yellow submarine wasn't invented there, but this was the problem. Like you have a submarine and you're making these little bubbles and you want to know what the effect of the bubbles are. This was Foldy's problem. Okay, so here's his method. So I already told you what the assumption was, that each scatterer, so now he's going to have n of them, each scatterer scatters isotropically. That means it sends waves out the same in all directions. That's what we mean by isotropic in this context. So that's what this is, right? So there are n scatterers. This is the incident field, whatever it is, right? There are n scatterers, and so now each one scatters like this, right? With some kind of amplitude, right? And so the problem now is to find these numbers. So Foldy wrote a very famous paper on this, but the famous paper is not famous for this. Right? In the paper, he's mainly interested in the propagation of underwater sound through bubbly liquids. So that means you've got many, many scatterers, right? But they're arranged randomly, right? So there's no way that you're going to be able to deal with that using this model initially, because this is a deterministic problem. You're supposed to know where all the scatterers are. Of course, you don't know where all the bubbles are, so you need some kind of randomization. And so what he did was he started from this, right, which takes one page in his famous paper, but then it's all to do with averaging and probabilistic theory, right, and make some predictions based on that. But this deterministic model is what we are going to need. Okay. So this is if you like, this is the representation for the total field. Incident field plus all the waves scattered that are coming off each of you in the audience here, right? You're all scatterers, right? So to make this work, you've got to find these numbers, right? And the way you find these numbers is by a kind of self-consistent scheme, right? So the idea is that you are sitting there, right? And so what do you feel? You feel the original incident wave, maybe there's a plane wave coming in, but you also feel the waves that he sends out, and the wave that he sends out, and the wave that he sends out, and the way that she sends out, okay? So you have to somehow make a self-consistent argument that I get all this stuff that comes in, right? That's going to be the incident field on you, right? Because you're going to have the actual incident field and all the other things that are being sent at you. Your job is to feel that and then send it out again, right? So to make that all work out, there's some kind of self-consistent scheme, because we have to make sure that everything works out together. So when you figure that out, you end up with an n by n linear algebraic system for these n numbers a sub j here. Okay? So it's an n by n linear algebra problem. So the idea is that if you accept the original assumption, which is that everybody scatters in an isotropic manner, then this accounts for all the multiple scattering that's going on in the room. Okay, and so that doesn't depend on anything to do with it's not specific to the configuration of the scatterers. Right? So now we're going to put these scatterers along a ring. Right? So that's the next step. Okay, so now we come back to the problem. Right? So I have all these little scatterers, right, and they're all arranged around this ring. They're equally spaced. Okay. So the spacing, the angular spacing, I'll call h. This is going to be suggestive to us later on, because we're going to encounter the trapezoidal rule, and h is going to be the spacing in the trapezoidal rule, right? So I get the linear system that comes out. This is the Foldy linear system. Here it is. Right? So it's n by n equations for these numbers a sub j. But now you see that the system matrix has a circulant structure. It has a particular structure which is to do with obviously the geometric structure here of the ring, right? The kind of what I see here is very close to what I see here, and I can figure out exactly what it is. So this, in general, right, this matrix C would have subscripts n, comma, j, right? But now, because of this geometrical arrangement, it only depends on the difference between n and j. And it's this difference, this circulant structure. So do you know what a circulant matrix is? Maybe I'm talking to the students here. I don't want to embarrass the faculty.
It's good to remind us.
Yeah. So a circulant matrix says this, right? It's a square matrix. Right? So I write down the top row, right? And then the next row is the same as the top row, except it's been moved by one step to the, say, the left. I guess it doesn't matter whether it's left or right. And then the next row is, again, I just shift it by 2 steps. So once you know the top row, you know all the other rows. Okay? That's what a circulant matrix is. Right? Much beloved of teachers of linear algebra. Okay, so that circulant structure is something that we'll exploit in a minute. Okay, so the other things that we know. So we know the thing on the right-hand side. This comes from the actual incident field, and what it is, it's the incident field sampled at the points. Right? And then the C matrix here has this structure. Right? So this H0 has come from the original assumption, right? And then this is to do with the distance between points, the distance between, say, this point and this point. Okay? So you see it's got this funny argument. Okay? One of the entries involves the G here. Right? So what was the G? G was the weighting that you give. So anyway, when the wave comes in and you scatter it, right, you have to multiply it by this G. If all the scatterers are different, then you'd all have your own G. Right? But because they're all the same, there's only one G. So I just call it G. In general, it would be G sub n or something like that. But because we're all going to be the same, right, it's the same constant. Okay, so it's a circulant matrix. Right? So I solve it. The idea here is that this can be solved explicitly, and it basically comes down to using discrete Fourier transforms. So I write down the solution. Okay, so here's the system. I solve the system. So I want to find the capital A's. I know the F's. I know the C's. So the solution involves the discrete Fourier transform. So that's what these twiddles are. These twiddles are the discrete Fourier transforms, and what they are is they are sums of the numbers here, right, multiplied by this object, and this phi is here. So n is the number of points, number of wires. Right? Everything I think else is clear. It's just they're just formulas. So here's the formula here. Okay, so so this thing here with the twiddles, this is the Fourier transform of the thing I want, right? And it's given in terms of the Fourier transforms of the two things I know, right? It turns out that for many of the things that you want to know, once you've solved this problem, many of the things you want to know, they are given directly in terms of these Fourier transforms, and you don't actually have to invert if you don't want to. So, for example, if you want to know the far field pattern, what you feel at infinity, then that's just you can find that directly in terms of these. Okay, but that's maybe not so interesting. All right. So now so we have the explicit solution, right? So now the idea is, well, tell me what happens now when the number of wires goes to infinity. So this is where we're trying to estimate what's going on. Okay, so this was the formula, right? So let's start with the F's, the right-hand side, right? So if I take the simplest physical problem that I can think of, which is I send in a plane wave, right, and it hits this ring of little wires, and I want to figure out what comes back. This is the simplest thing I can think of that makes any kind of sense. Then the F's are such that when I compute this Fourier transform, right, I get a sum, and it comes out looking like this. And now I've tried to write it in terms of this parameter h. So remember what h was? H was the angular spacing between two neighboring wires. Right? Here it is. Okay. So when I stare at this and I think, well, that looks a bit like a trapezoidal rule. Right? How does a trapezoidal rule work? Of course, I'm talking to the students here. Right? So I tell you what. Let's review trapezoidal rule. So this is almost the first rule you learn about when you talk about numerical ways for evaluating integrals numerically, or maybe in calculus 1. So you say, if I want to estimate an integral of a function f over here, I take the interval 0 to 2 pi because that's the one that's of interest to us. Then what I do is I compute this formula here, right? So there's a bunch of terms here in the middle with a weight h. And then there are two endpoint contributions which have got a half on them. Right? All remember that? Yeah, of course you do. Okay, but now if in the special case where the function is periodic, so that the value at one end is equal to the value at the other end, right, then these two values here are the same. So I put them together, and now it looks like this. Okay? So now the sum looks almost exactly like what I showed you just now. Right? Oh, so we'll come back to that in a minute. but one thing to notice here is that if the function f is 2 pi periodic and it's a smooth function, right, then this is the best quadrature rule there is. Right? You don't want to use Gauss rules or anything else. You can't do any better than this because it converges exponentially fast. Right? Big assumption, though, the function that you're integrating is periodic with the length of the range of integration, right? And it's a smooth function. It's got to be really smooth, analytic function. In fact, there's a whole paper on this just come out, 70-page paper on how good this is. This is not an advertisement, right? This is. Okay, so now let's come back to where we were. All right. So remember what our job was, right? We're trying to find the exact solution of this problem, and we want to know what happens when n gets big. Right? So we have a formula for this thing, right? And I showed you that it looks like this, but it is this, right? And I've massaged it so that it looks like trapezoidal rule. Okay. So I've written it now like this. Okay. So if I divide by capital N, right, then I get something that looks exactly like what we just saw, trapezoidal rule. Okay? Where the function now that we're sampling is this simple combination of exponentials. Right? So I just massaged it so that it really looks like trapezoidal rule. Now, because this function f that we're dealing with, you can't get a function that's much nicer than that, right? From the point of view of its analytical properties. It's smooth, it's 2 pi periodic, it's a beautiful function. Right? That means that the trapezoidal rule converges incredibly fast, exponentially fast. Right? So that means that this function here, this thing that we're working out, in the limit, as capital N goes to infinity, that says that I do my quadrature rule with more and more points, right? More and more accuracy. Right? Then I get the value of the integral, right? This is the job of the trapezoidal rule, is to estimate this integral. Right? We came at it from this end, right? So this I can compute, and I do the integral, and it comes out to be this, right? After a bit of work. Right? This is what you get in the limit. So in the limit, right? The error that I haven't bothered to write down is exponentially small, so it goes to 0 incredibly fast. Right? This is very, very heartwarming, right? Because it makes us feel like this sounds good, right? Compared with what Maxwell showed you. Exponential convergence. Right. So now we work on this bit. Right? So we've done this bit. Everything's lovely. Now we look at this one. Right? So now we still have something that looks like trapezoidal rule. Okay. So now the problem is. So this all looks really nice. Right? There's a term left over which we'll deal with in a minute. The function that it looks like that we're trying to integrate is this function. I call it v of theta. Right? So this function, it is 2 pi periodic. Great, right? But it's not nice, right? It's not a nice function. And the reason it's not nice is that if I choose to evaluate it at the endpoints of the integral, right? If I think about it in terms of the trapezoidal rule, the function that I'm trying to integrate is infinite at the endpoints. So trapezoidal rule is really bad, right? Because you wouldn't be able to evaluate the function at the endpoints like you usually do, right? So that spells trouble. Okay? So in effect, what we've done here is it looks like we've used the trapezoidal rule, right? But we've ignored the bits that come from the two endpoints, which is just as well because there are infinities there, right? So you've ignored them, right? So if you look in books on numerical methods for evaluating integrals, right? And the one I'm familiar with is by Davis and Rabinowitz, his famous book on numerical integration. This method where you kind of ignore the endpoint contributions, it has a name, and it's called ignoring the endpoint contributions. So it turns out, though, that this method, which is bad, right, has been analyzed. Right? And it was fortunate for me that this had been done, because I'm not a numerical analyst. Right? And there is a theorem that says that it converges. This does converge. So as n goes to infinity, this will converge. Right? But the error is very bad. Right? So here's the error. Right? Think about if you were thinking about quadrature, n is the number of points. Right? So the error it does go to 0, right, as n goes to infinity, but really, really slowly. Right? So if you wanted to use this as a quadrature rule, you'd be mad. Right? This would be a crazy thing to do. Right? But we had but think about how we did it. That wasn't our task. Our task was here's an integral, compute it. Right? The task was here's the discrete problem. tell me what that discrete problem approach is as the number of points in the discrete problem goes to infinity, right? And it does approach what you might expect, the continuous limit, right? This is going to represent the problem without the wires that I talked about at the beginning, right? But the convergence is incredibly slow, right? And I should say also that this is not a conservative estimate. It really does go like this. So you can actually estimate what this term is and get rid of the big O here if you want to know what the error really is like. So you can do that. Okay, so when I put these things together now, so you remember that the F's behave really nicely in the limit and the C's behave really badly in the limit. Right? You do get convergence, and this is what you get. And this is exactly what you would get if you solve the problem of scattering by a big circle of radius b. This is exactly what you get. So it does converge to the right intuitive answer. Right? But the convergence is very slow. Okay, so what I said here, yes. So, so for example, if you, for example, compute, all right, so I take the following thing. I take a ring of wires, right, all these rings like this, and I estimate the field right at the middle, right, of the ring, right. So you can estimate how what you expect is that is going to go to 0 as n goes to infinity. And sure enough, it does. Right? It does go to 0. But it goes to 0 very slowly by the same rate here. To me, that was surprising. I mean, I don't know whether that's surprising to you, but it's surprising to me. So this is my last slide, so I can spend a few minutes, I think. What time does the wine come? Okay, so I observed this slow convergence with n. You see that it contrasts with what we saw with the Maxwell problem, the infinite row problem, right? But here, it's not quite the same, right? So the Maxwell problem that I mentioned with the infinite row of wires, right? We see this exponential convergence. We see this exponential decay as a function of distance from the row of wires. Right? Here we're seeing this very slow convergence as a function of the number of wires. Right? But nevertheless, this is the problem that you would be interested in physically, right? If you want to, so you know that these kind of shields, these cages are used for all kinds of applications. So, for example, they were used in Rome when they were choosing the new pope, right? So the room where all the bishops and cardinals were doing all whatever they do, they weren't allowed to use. Well, they were told not to use their cell phones, but you can never trust the cardinal, so they had to surround the building in a wire mesh so that they couldn't send things out, right? So I've done the similar calculations for Laplace's equation, and it turned out that this Foldy's method that I just discussed, it was invented for acoustic scattering problems, bubbles, but it doesn't seem to have been used. There doesn't seem to be a version of this used for Laplace's equation, which you'd think would be simpler, right? But it turns out I haven't found anybody that's done this before. It would be interesting to push this to scatterers that are not soft, right? So the reason that's interesting is that in the world of sound, many scatterers are not soft. So most rigid objects, right, they're poorly represented by saying that the boundary condition is u equals 0. Foldy's method is then not good because it says that because Foldy says you are sending waves out isotropically, the same in all directions, right? But we know from kind of classical asymptotic approximations that if you have a hard object, so that says not u equals 0 on a circle, but maybe du by dr equals 0 on a circle, then that scatters like a dipole. So there's a definite angular dependence on the scattered field. So you can extend Foldy's method to cases like that, but it's more complicated. And so I haven't done that. I haven't used that extension for this problem, but I probably should. It would be great if you could do problems like this in 3 dimensions. So this is a really interesting problem, right? So now you say I take a sphere, right? And on this sphere I distribute all these point sources, if you like, or point scatterers. But there's no analog of a circulant in that world. No analog that I know of. And in fact, this is a very hard problem, knowing how to. It's called Thomson's problem. So if you take a sphere and you want to put sources on it, think about the gravitational problem, if you like. Try to put them on it so that you minimize the energy of this configuration. This is open problem, how to do this. Right? So it's known what to do. It's like one of these problems where you can solve it for, say, you say, well, if you give me 10 points, I can tell you where to put them. If you give me 11, I can tell you where to put them. But there's no formula. You can do the optimization problem. The people have done that and spent lots of time on it. That's called Thomson's problem after Kelvin. But the problem is interesting. The three-dimensional problem here would be interesting, but I have no clue how to do that. And this thing has just been published if you want to read more about this. But I think I probably will stop. Thank you.
So now we open a discussion and questions. Okay.
Your original picture belies your solution, or I'm not understanding something. It looked like the grid that your friend with the spark coming down was incredibly crude in terms of spacing of his little wires.
Yep.
And you said he walked away unscathed, but you're telling me that the wires need to be really close together for the solution to work.
Well, I
disconnect here.
Well, it may be that the model I used is too crude. Right? So I don't understand how this works. I mean, apparently he did survive. This is like a snuff movie of some kind. So I don't know, and I don't think people understand this problem, and it's very surprising to me that there isn't a proper theory for these problems. You can see the wire here is a much more complicated mesh as well. So I don't know what the effects of 3 dimensions are, for example. I mean, you can see I'm a mathematician. I've picked the simplest problem I could think of that might be plausibly related.
Is that a real picture or animation?
I'm sorry, you have to use...
I have no idea if that's a real picture.
With that, I will ask a different question.
I just like the picture. It's a good picture, right? It's got you interested.
My question is this. You said that this Foldy method is an approximate method. But then it leads to a singularity of the endpoints, because you divide by the sum total. Is the singularity an artifact of that approximate method or not? That's one thing. The other way is how do you measure that? This is from the direction of the instant depth?
No, so the direction theta doesn't depend. It doesn't depend on where the instant wave is. That would affect the what I called F, so the right-hand side. That's where the instant field comes in. Right? So that wouldn't matter because you can just you can basically rotate the problem.
So this is kind of symmetric problem rotationally. So why?
Yep.
Singularity occurs at one point, and if you rotate the coordinate system, it should occur at a different point.
Well, it's because if you try to evaluate, so you have all these Hankel functions, right, and they involve the distance between 2 points. So if you try to evaluate it when the 2 points are the same, right, so if you like the self-influence bit, that means you have to evaluate the Hankel function at 0, and the Hankel function has a logarithmic infinity at 0, and that's exactly what we see. And it's that turns up.
Independent how you rotate.
Yes. Yeah, definitely.
Maybe I'll ask a follow-up question on this Foldy method. Was it verified somewhat by direct calculations?
Yeah, so people have used Foldy's method for other deterministic problems and compared them.
With exact.
Yep.
So if you were to extrapolate this ignorantly to 3D, would you get something like 1 over, or not 1 over, but Ka squared perturbation?
I don't know. I don't really know. I don't really know how to start going to 3 dimensions. That's the trouble. I mean, I know how to set the problem up, but I don't know how to where to put the points. You see, my starting point was, okay, I take a ring and I put the points equally spaced. I don't know what the analog of that is in 3 dimensions.
Because if you do, let's say, if you have many dots inside a circle,
right,
then the effect will be kind of like a Ka squared.
Probably,
in 3D.
yeah. Yeah, probably.
Yeah, we have that result. So it's
would be a three-dimensional problem for cylindrical cage easier to solve than for spherical?
You mean
Because
taking
you see-
you mean taking account of the effect of things going this way?
Yeah, like, for example, you imagine
This
that you
man
have
here?
dots in...
I don't know. So you mean really where I actually have a cage,
Right.
like a cylindrical cage,
Right.
but a forcing that's obviously not two-dimensional here, right? I don't know. I think there's lots of things that you could try, but I've...
And maybe last question before we... If there is any. If not,
Students always sit at the back because of electrostatic repulsion, right?
if not, let's join me in thanking the folks and welcome to the reception. Okay, now it's time for wine and cheese.